Hi everyone, we're finally at chapter 10, which is thunderstorms and tornadoes, the fun stuff about weather. So I am just going to go over the things that might be confusing in the book because I figure you'll read the book at this point because it's very interesting. There are some things that I think that are a little bit complicated in the book, so I want to point those out to you. And first I want to point out to you that the reason you have the cover of your text is that is a beautiful wall cloud, and that is what we're going to be getting into today and learning about a wall cloud and the difference between that wall cloud and this shelf cloud. All right, so we're going to be learning about what those clouds tell us about thunderstorms and tornadoes, and that tornadoes evolve from severe thunderstorms. So let's get into it. Thunderstorms come in different severities. They all have some things in common and some things that are different. So if you think about ordinary thunderstorms that we have at 4 o'clock, 5 o'clock in the afternoon, and if you think about thunder snow, which we actually had a bit in during March of this past year, and if you think about complex thunderstorms that arrived with a hurricane last week, then you start to notice that they have several things in common. And one of them is that they have a moist air mass, of course. And so you're noticing that. You might wonder about the temperature of the air mass, but you're being sophisticated enough now to know that warm air fuels a storm. So even in the middle of a thunder snow, you know that there's warm air in that cyclonic rotation that is producing some thunder snow as well. So you know that these things have in common moist air masses, and there is some warmth to the air masses. In addition, you know that some things are in common. They have lightning and gusty winds and precipitation, of course. Sometimes flooding is likely with severe thunderstorms, and you know that during the summer you'll get hail out of those storms sometimes, and during the spring, but you won't get hail during the winter. So we're going to separate what they have in common and what they are having as far as their differences. When it comes to those scattered thunderstorms at 4 o'clock in the afternoon and thunder snows and big complex thunderstorms, they are all convective storms, and they all develop because of uneven heating of the ground. Remember, the sun does not warm the air. The ground warms the air. You might say, well, if it's thunder snow, but you know that there is a warm air mass that's involved in a precipitative storm. So you know that that warm air mass is involved. Even if you can't feel it on the ground, it has lofted above and is condensing. Also, these storms all need a conditionally unstable atmosphere. And remember, a conditionally unstable atmosphere means that parcels need a forced lift by convection or by topographical lifting or by frontal lifting or by convergent lifting. And after they are forcibly lifted through a stable atmosphere, because they wouldn't be able to lift by themselves in a stable atmosphere, then they condense, and then they might need a little bit more lifting from there as they start to condense and warm their parcel to the point where they are warmer than the atmosphere around them at higher levels. And then they can rise on their own without lifting. They can rise on their own in an unstable atmosphere. So they started in a stable atmosphere where they needed a forced lift. Then they condensed. Maybe they needed a little more forced lifting after that until they were warmer than the atmosphere and they could rise in an unstable atmosphere. That situation is called a conditionally unstable atmosphere. All right? Depends on the conditions of the forced lifting. If you look at thunderstorm distribution and days per year, you will note that Miami is known for 1 out of 4 days, we'll have a thunderstorm in the afternoon. So very high levels along the Gulf of Mexico. Obviously, there's a warm, moist air mass there. And there are also high levels. Look out in Colorado. You've got a patch out there that is associated with a low system that is called a Colorado low. And you might say, well, where is the warm air mass that is moist in Colorado? There's no moisture around there. During the summers, that moist air mass that you see trending to the west is what's fueling those thunderstorms right out of the Gulf of Mexico. So you see that trend, and that trend hits Colorado. Hailstorm distribution really focuses on Colorado because you've got colder air up at those altitudes. So you can have a very mixed atmosphere between the warm, moist air that is coming out of Mexico, the warm, dry air that is coming out of Mexico, and the warm, moist air that is coming out of the Gulf of Mexico at the higher altitudes really does produce hailstorms in the Colorado area. Now, I wanted to show you another type of sounding now that you've gotten used to sounding. And this other type of sounding is called a Skew-T sounding. It's called a Skew-T sounding because the temperature lines, the T lines, are skewed on this sounding analysis. So prior to this, we were looking at temperature lines that went straight up. Now we're looking at temperature lines that are skewed to the right. The reason we're looking for those is because that is a form of analysis that really lends itself to picking out storms very readily. You can tell how unstable the atmosphere is with this type of analysis. It's much easier to tell it right off the bat than to look at the temperature patterns that we were looking at on what we call the Stuve sounding, which you learned on. You learned on Stuve sounding. I'm just introducing Skew-T soundings because of this. What you notice here in this conditionally unstable atmosphere is that this parcel had to be lifted up in this area by some force lifting, and then it had to be lifted up a little bit more, but then it got warmer than the atmosphere in red around it, and it could convect up on its own, all the way up to the stratosphere. So this is a big day for thunderstorms, and this is in the springtime as well. These Skew-T soundings tend to accentuate what we call convective available potential energy. And you can really see the difference between the temperature and the unstable atmosphere that's allowing that parcel to rise so much. So I wanted to introduce that to you. And I also wanted to go over the fact that that sounding was one site vertically all the way up in the atmosphere, taken twice a day. And another type of weather observation that we can see thunderstorms on is one location at the surface only, taken hourly each day. And look what you can observe here. You can observe hourly, you see the hourly measurements here of cloud coverage, of wind direction, of wind speed. And normally you would say, well, that front came in because the wind changed direction. And you'd know exactly when the front came through. But in this case, you know something happened, but you can't really tell because the wind is so gusty. So what other measurements can you go to? Well, you can really go to lightning and intense lightning, like you might notice here, where the arrow is down on a couple of angles. That's where you know that the lightning was very intense in there. There's more folds to that lightning mark than there are here. So where the lightning is very intense, it's usually right when you know that your storm is hitting. It's kind of interesting here. The wind was coming from the southwest, then the wind stopped dead. calm before the storm. And then it picked up again. So we are going to say that the front line was where the lightning was most intense. And you notice there that right before then, the winds got really, really gusty. So that's where we can name that front on a meteorogram. These ordinary run-of-the-mill 4 o'clock thunderstorms have the same life cycle of updrafts and downdrafts when they're small thunderstorms and when they're big thunderstorms. And we're going to get into the specifics of that. An ordinary thunderstorm will have very little wind shear. It will just convect up and develop its downdrafts and come down. A multi-cell thunderstorm, which we will go into, has moderate wind shear. A supercell thunderstorm, which could very likely become a tornado, has dramatic and very strong wind shear. Ordinary thunderstorms tend to be about 1 kilometer wide, tend to come and go. 5 o'clock, 6 o'clock, they're gone. As I said, very limited wind shear. Very well known in Miami and in Orlando, Florida, coming in off the Gulf of Mexico, coming in off the Atlantic Ocean, convergent lift, take it atmospheric, and it comes right back down again. That's an ordinary thunderstorm and an example of one. And what I'm going to do is go through the phases quickly. The cumulus stage of this is when the warm, moist air convects up and it moves into dry air up top. If you watch a thunderstorm at 4 o'clock, you'll see that there will be evaporation up at the top. And newly moist air will be around the top, condensing into other little clouds at the top. I saw this yesterday. Then those new little clouds will evaporate away again, moisten the air around it. That air will condense because it's moist. Then that dry air will evaporate those again. This is heating the parcel and leading the parcel higher and higher. So that is the cumulus stage. The mature stage is when you might see an anvil top because you've raised this thunderstorm up to the stratosphere. That latent energy of that consistent condensing and moving higher and higher was boosting this up to the atmosphere. As you get there, you are also evaporating around the entire side of the very high thunderstorm that's in dry air. And when that happens and you evaporate, remember evaporation is a cooling process, you are cooling the parcel now way up high. So you're going to start to get some downdrafting from the more dense air that is within the parcel. So that is why I flipped this over for you, because it's going to help you in the long run, that you might get on the leading edge warm air up into the anvil, but then all this air up here is very dry. It's going to evaporate off and cool and lead to the downdraft. This can form a very cold gust front on the way out. We noticed that just last week with the tropical storm moving in. That's what caused all the damage. The dissipating stage is when the gust front moves away, the downdraft empties out the storm, and you are then left with a storm that you can see through because the downdraft just emptied out one whole side of the storm. That's really a very dramatic shot right there. So I'll see you on the other side.